This previous method, this previous procedure will give us a decision, so it will tell us yes or no as an answer to our research question, but it will not give information on the strength of the evidence for your decision. So it will not tell you how strongly you are rejecting the null hypothesis. This extra information can be obtained through p-values. So p-values are another method to determine whether or not you reject the null hypothesis, but it also tells you, in a way, how strongly you will reject the null hypothesis. Take a look again at the distribution of captopril, the example captopril, and assume that our test statistic was not the blue line, but the green dotted line. In that case, it is clear that the green line is still rejected. So if we find this, we will still reject the null hypothesis, but it is less strongly rejected than when we found the value of minus 8.12, which was the blue line, because the blue line is farther away from the center. So it is more likely to find the green line than it is to find the blue line. So we will more strongly reject the null hypothesis in the case of the blue line than in the green line. To quantify this strength, we can look at the probability to find a value of our test statistic as extreme as the one that we found. Remember, in our case, the value that we found was minus 8.12. So as extreme as minus 8.12 means that it has to be smaller than 8.12. So it has to be farther away from the center than 8.12. But we are here in a two-sided alternative, so it also has to be larger than 8.12. So on the other side, it has to be in one of the tails. So we have to look at the probability in both tails. So what we do is we calculate the probability to have a value for my test statistic as extreme as minus 8.12. But since we are looking two-sided, it means basically that my absolute value of a test statistic has to be at least 8.12. So we look at the probability that the absolute value is larger than 8.12, or you can keep it separate. You can also look at the probability that my test statistic is smaller than minus 8.12, plus the probability that my test statistic is larger than 8.12, so that covers the left plus the right tail. Or you can say, since both tails are the same, it is a symmetrical distribution. This is 2 times the probability that t is larger than 8.12, or 2 times the probability that t is smaller than minus 8.12. If we then calculate the p-value for the captopril example, we find a value which is less than 1%. So it is a very small probability. It is therefore very unlikely that the null hypothesis is true. Remember, we are testing as if the null hypothesis is true, so under the null hypothesis. And here there is almost no evidence to find such a value of minus 8.12 merely by chance. So the value can hardly ever be found by chance, and so we will reject the null hypothesis and we will go for the alternative hypothesis. So the p-value is the probability to find purely by chance, so only due to randomness in the data, under the null hypothesis, a result for the test statistic that is at least as extreme as the observed result. In this case, at least as extreme as the observed result means that it has to be farther away from the center in the direction of the alternative hypothesis. So depending on the test, if it is a one-sided left, one-sided right, or a two-sided test, you will look in different directions, but you will always look away from the center of the distribution in the direction of the alternative hypothesis. The smaller the p-value is, the more the results will contradict the null hypothesis, and so the more informative, the more significant the conclusion is. Why? Because small p-values, if we look back at the previous slide, mean very small blue areas, and so the test statistic that we observe is far away from the center, so it is more extremely rejecting the null hypothesis. There is more evidence that the null hypothesis is not true. How will we decide whether or not to reject? Well, we compare p with the significance level that we have chosen before. So p is a probability, and the significance level was also a probability. So the significance level was the probability of making at most alpha% of type 1 errors. And so if my p is smaller than alpha, then we reject the null hypothesis. So for every test, you can easily check through a p-value. You compare the p-value with the alpha value. If p is smaller than alpha, then you reject the null hypothesis. Let's also illustrate this visually. So plot again the density function, and add to the density function the parts that we know. So we add the threshold values, the quantiles. If we have these quantiles, we know alpha, or basically if we have chosen alpha, we know these quantiles because they are linked. It is the quantile such that we have a rejection region of alpha percent. If we then look at our decision rule in the case of the p-value, we had a decision rule that we reject if p is smaller than alpha percent. So if the probability to find a value as extreme as my test statistic is smaller than my alpha, so this means that the red area which is more extreme than the test statistic, has to be smaller than the blue area which corresponds to alpha 5%. So it also means that my test statistic has to be in the rejection region, and so p smaller than alpha is basically the same as saying my test statistic is in the rejection region, and so I will reject the null hypothesis. Using the p-value, you can also sort of choose your significance level yourself. So instead of fixing an alpha level before you start your test, you can look at the p-value, and depending on the p-value, the value of the p-value, you can give it a significance based on how strongly it is rejected. So if my p-value is larger than 10%, we will say it's not significant. There is weak evidence for rejection. If it is between 5 and 10%, we call it suggestive or marginally significant. If it is between 1% and 5%, it is a significant effect. So there is significant evidence to reject the null hypothesis. Between 1% and 0.1%, it is strongly significant, and smaller values of p, we call them extremely significant. So a p-value will lead to a uniform testing strategy. You can compare different tests, and you can compare the p-values to one another and say this test is or has a stronger result than another test. In our case, the mean systolic blood pressure decreases extremely significant after the administration of captopril. Why? Because our p-value was smaller than 0.01%. However, also with p-values you have to be careful. So you have to watch out when you only see a p-value in a paper or in a report. Take the following example. So Lutra et al., they did a research on radiotherapy for breast cancer, and they gave radiotherapy to 25 breast cancer patients at the start of the experiment, then again after 1 week, after 3 months, and after 1 year, and then they checked the effect on the lung function. So they looked for changes in the lung function, and if you see a positive number, it means that there is a good effect, so the lung function, the respiratory function is increasing. A negative value means that the lung function is decreasing. So after 1 week, they found a mean change of 48, which means basically that the lung function increased, it became better, with a p-value of 0.13. After 3 months, they found an effect of minus 63, so a negative effect, and after 1 year of minus 49. So minus 49 is already less negative than after 3 months. So again, after 3 months, so between 3 months and 1 year, it seems that the lung function has increased again, has become better again. They did report the p-values, but they did not indicate which hypothesis they were testing. So you have no idea if the test is one-sided or two-sided, nor an idea about the direction of the test. And if you then would recalculate the p-values, if you would take the data and try to find these p-values back, then it will become clear that the tests are indeed one-sided, but that they are not consistent in the testing that they are doing. So the direction of the alternative hypothesis changes in function of the data. So sometimes it is a left one-sided test, sometimes it is a right one-sided test. And normally if you report like this, all 3 tests should be the same, so they should all be left one-sided or right one-sided test, and not a mix. So if you only have p-values and you don't get any idea about alternative and null hypothesis in the paper, be very careful and be conscious that there might be some problem or might be something that they are trying to hide. Important is also that if you choose for a one-sided or a two-sided test, as well as the direction of the one-sided test, you must do so in advance. So you have to determine this before you do the test in order to not increase the risk on type 1 errors. Also, it is not allowed to abuse the data, so you will not first do the test and then decide based on what you see in the test what your research question would be. This is sort of being fraudulent, because you would adapt your research question to what the test is giving you. So you would make sure that you are always having a yes answer on your question by first checking what the answer would be before posing the question. Often a priori, so beforehand, it is not known in what direction the effect should be expected, and then it is also very difficult to choose for a one-sided test, and therefore a one-sided test is usually not appropriate. Effects can also be contrary to expectation. So for example, N9 has now been proven ineffective against HIV transmission. The possibility of risk with no benefit indicates that N9 should not be recommended as an effective means of HIV prevention. What they did here, or what they wanted to test, is a medicine against HIV transmission, and they had expected that it would be a positive result. So preliminary studies had indicated that it might be effective, but once that they did the test on a larger scale, so they collected the sample, they performed the test, then it became clear that after all there is no effect. So you can expect an effect, but your test might prove you wrong, so it might prove that there is absolutely no effect. As we stated before, the direction of the effect is usually unknown, so we don't know if it would be an increase or a decrease, a positive or a negative effect, and so usually a two-sided test is more appropriate. Also, instances such as the FDA, they demand that tests are performed two-sided and not one-sided, so they demand that you look for an effect and not for a positive or a negative effect. The only thing when you do a one-sided test is when you are not interested at all in one of the directions. So, for example, if you monitor pollution, you want to know if the pollution exceeds a certain threshold. That's interesting, but if my air quality is good, perfect, or superb, I don't care. I want my air quality to be good, so I want to be below a certain threshold of pollution. So I have here only a one-sided interest. I only do a one-sided test in the direction that I'm interested in. I will not test for good, perfect, better, best, superb. I will just see, is my pollution too heavy or not?